Hello everyone, this is Dr. Webb. So in this video we're going to talk about line integrals. So let's get some terminology down first. So we're going to be integrating over curves, over smooth curves. So let's talk about what a smooth curve is. So a curve is smooth if there exists a differentiable parameterization such that the derivative is never equal to the zero vector for all t. So we talked a little bit about, earlier on in the course, we talked a little bit about smooth parameterizations. And so this is having r prime never equal the zero vectors is what a smooth parameterization is. And so curve being smooth just means that it has a smooth parameterization. And then a curve is oriented if it has a direction along it. And so any parameterization gives an orientation because the parameterization has a sort of a beginning and an end. It has a way in which it goes through the curve. And we're going to say a vector field is continuous. That just means that its component functions are all continuous. So if it's a vector field on R2, that means that it's the function for its x component and for its y component are both continuous. Okay, so the setup for these line integrals is that we're going to have a continuous vector field called f, and C is going to be a smooth oriented curve. So there it is. Okay, so our vector field here are the colored plots, colored vectors going through, and then we have C is our thick black curve passing through it, and you can see the arrows along C are giving the orientation, right? And so we can say C starts at this point, let's call it x naught, y naught, and it goes up to this point, x1, y1, and so at each point along here, say, f has some value, and so you can kind of come up with f looks like some vector like that for each point along the curve. Okay, so this is the underlying situation that we have. Okay. So now we're going to define the line integral. So the line integral, we're going to start off with a continuous vector field f and C with a smooth parameterization, r of t, just like we saw in the picture. Okay, then with the line integral of f along C, and so the notation is going to be the integral over C of f dot dr. And what that really means is we're integrating the vector field with the parameterization of the curve plugged in, and then dotting that with r prime, the derivative of the parameterization, and then integrating that from A to B. Okay, so this is what the definition of a line integral is. So let's put this in this picture. What exactly is this talking about? Well, let's focus in on what we're really integrating right there, right? So if I pick some point on the curve, and actually this is a good point right here. So what's r prime talking about? So r prime is, remember, it's going tangent in the direction of the curve. And so that's r prime of t at some point. In this picture, we have a nice view of what the vector field is at that point. And so this is f of r of t at that point. And so then what we're doing is we're then taking the dot product of these two vectors. So we're looking at the dot product of f at this point and r prime of t. And so if you look, these two vectors are roughly in the same direction. And so the dot product there is going to be positive. And then we're integrating that, so that means that we're adding those together all the way along the line. Okay. So that's what the integral is saying. Why would we ever want to do something like that? Okay. So here's, as it says, a hand-wavy idea underlying where these are coming from. Okay. So the central question is at each point we're thinking about how much f is in the direction of the curve as we move along. Right? So how much is f moving in the direction of the curve? Well, so if we're talking about the direction of the curve really is r prime. This is telling us direction of the curve. So if we want to know how much f is going in the direction of the curve, this really is talking about a component, right? And so this is really talking about the component of f in the direction of r prime. And if you recall from earlier on when we talked about dot products, this component is you take f, dot it with r prime, and then you divide by the magnitude of r prime. Now I should say in all of this derivation right here, I'm dropping my variable t for the most part, just to make things look a little bit cleaner. Okay, so this is telling us at that point how much f is going in that direction. Okay. So now what we're going to do is we're going to break up the curve into bunches of little bits, call them delta r's, and then we're going to think about that component, so that length being multiplied by delta r. So that length being delta r long, so that's the f times the length of that portion, or the part of f going in the direction of the curve times the length of that portion, and then we're going to sum those all up together. Right? So that's going to look like taking this component that we saw before and then multiplying it by this absolute value of delta r that's talking about the length of the part of the curve from when we broke it up, and then we're adding these all together. Okay. Well, one thing to note about delta r, so this is sort of, think about the length of delta r, this is kind of talking about the length of r, some difference, t plus delta t minus r of t. That's really what delta r is talking about. Well, in this right here, this looks like close to the definition of derivative. So this is approximately equal to the length of r prime of t if we had delta t on the bottom, but we don't, so we got to multiply delta t over there. Okay, so delta r, the length of delta r is really is sort of the length of r prime of t times delta t. And so we can plug that in. But now we see in the definition of component, we have an r prime on the bottom. In our sum right now, we have r prime on the top. Those two are going to cancel each other off. And what are we left with? F dotted with r prime times delta. And so plugging that in, this sum of multiplying the component times the length of these bits of curve is going to turn into just the sum of f dotted with r prime times delta t. And so that's what we derived on the last slide. And so now, this is a Riemann sum. We take the limit as n goes to infinity, and this is going to turn into this definition of a line integral that we had before. So this is our line integral of c f dot dr. Okay. Okay. So that's the hand-wavy derivation. Why the hell would you ever want to do something like that? Well, one immediate application of line integrals from physics is if we let F be a force field. So at each point that's representing some force, and we have R of t is representing the path of some particle affected by the field. And so that means that at each point along there, the force is being applied to the particle. Then what the line integral is going to be is that's going to tell us, that's the definition of what the work is of F onto the particle. So that's the work applied by F onto the particle as it was moved. So if the particle is moving in the same direction as F, that means F is contributing to the particle's motion, and so the work will be positive. If the particle is moving against the force, well, that means that the work's going to be negative, and so that means that other forces had to have been applied to move R the other way. Energy had to be expended to get the particle to move against the force. So one thing to note is that the line integrals don't depend on the parameterization of C so long as the orientation doesn't change. And so you can use a different smooth parameterization for the same curve in a line integral, and you get exactly the same value out of it. And if you go back to our derivation, that kind of becomes that the component that we choose, R prime, all that's important about R prime in the component is its direction. That if we swap it out for a different parameterization, that's going to change R prime, but that doesn't really change the component. And then breaking it up over those different chunks, that all of that is going to cancel off at the end. So switching a parameterization for a curve doesn't change the value of the line integral, and so the line integral really is inherent to the curve, not so much the parameterization. Okay, so here's an example of a line integral. One thing about line integrals that I always feel is that it's much harder to figure out sort of intuitively what they're saying than to actually calculate them. Especially compared to double or triple integrals, line integrals typically are pretty easy to calculate. So we're integrating, our vector field is y squared comma 2xy, and our curve is parameterized by t comma 2t from 0 to 1. And so if we're thinking about this on the xy plane, this is just going from starting at the point 0, 0, and going straight to the point 1, 2. And so that's our curve, C. Okay, so we need R prime. And so R prime here, derivative of t is 1, derivative of 2t is 2. So that's simple enough. We need to plug R of t into F. And so my y component is 2t, so 2t quantity squared is 4t squared. 2xy is 2 times t times 2t, and so this is 4t squared comma 4t squared, and that's nice. Okay, and so then our line integral, so we're integrating from t goes from 0 to 1 of the dot product of 4t squared dotted with 1 comma 2 dt. And so this is 4t squared plus 8t squared dt So we're integrating 12t squared. And so the integral of 12t squared is going to be 12 over 3 is 4t cubed from 0 to 1, which is going to give us 4. Okay. So you can see it's a little bit of work, but this is a lot simpler than doing double or triple integrals. This really is when you get down to it, it's just a simple Calc 1 integral. Okay, so now we're gonna integrate the same vector field, but now our curve is going to change. So now our curve, it's still starting at the origin and still going to the point 1 comma 2, but now the parameterization is t comma 2t squared, and so that's going to be moving along a parabola between the 2 points rather than on a straight line as we had before. Okay, so we're going to go through the same process. So I need r prime of t. In this case, r prime of t is going to be 1 comma 4t. We need to plug these in to f again. So f of r of t for a new parameterization is going to be 2t squared. Quantity squared is going to give me 4t to the 4th now. And then we have 2 times t times 2t squared for the y component. So this is now 4t to the 4th, 4t cubed. So our line integral f dot dr is, we're still integrating from 0 to 1, and we're dotting 4t to the 4th, 4t cubed, dotted with 1 comma 4t, dt, and so 4t to the 4th, plus now 4t cubed times 4t is going to give me 16t to the 4th dt. And so really we're integrating 20t to the 4th. And so when we integrate this from 0 to 1, the integral of t to the 4th is going to be t to the 5th over 5. So 20 over 5 is going to give me just 4 again. So it'd be 4t to the 5th from 0 to 1, which just gives me 4. Right? And that's the same thing that we got in the last one. So is that a coincidence here that we got the same values? The answer to that is no, and that's because of what's called the fundamental theorem of line integrals. Okay, and so what the fundamental theorem of line integrals says that if the vector field that you're starting off with is conservative, so remember conservative means that it is the that you can consider it to be the gradient of a potential function, and so our potential function here is phi, and C is a smooth, piecewise smooth oriented curve. So piecewise smooth just means that you can break it up into a bunch of connected smooth pieces, and it's starting at the point x0, y0 and ends at x1, y1. So C here looks like it might have some hard angle, maybe another hard angle, and ends there. x1, y1. So that's our curve. Then what it's saying is that the value of the line integral of f is going to equal just the value, the difference between the values of the potential function at the end point, so this is the end, minus the beginning. And so this should remind you a lot of the fundamental theorem of calculus. In fact, it's just sort of the form of the fundamental theorem of calculus for line integrals. Okay, so where is this coming from? Well, so if we have f is our vector field, and it's conservative, and so it is the gradient of phi, and let's let our curve be parameterized by r, which has components x of t and y of t. Okay. Well, so then what our what our line integral really is if we're integrating f is the same thing as a gradient, so really we're integrating the gradient there. And so then if we plug that in and take the dot product, well, r prime really is dx dt dy dt. The gradient is the partials in terms of x and y. When we dot them together, we get the partial of phi over x times dx dt plus the partial of phi over, in terms of y, times dy dt. Well, this should look really familiar. This is what we get when we do the chain rule on d phi with those plugged in. And so let's swap that in. And so really we're just integrating the derivative of phi once we plug in x of t of y of t. So this derivative now makes sense, because once we plug in x of t and y of t, phi is then just a function of t, so we can take the derivative in terms of t. And so this right here is coming from the chain rule. And then what happens when you integrate a derivative? Well, the fundamental theorem of calculus tells you just stick in the endpoints. And so that's the end of it. So this really is just a form of the fundamental theorem of calculus applied to line integrals. Okay. And so one of the interesting things to note about this is what this means is that if f is conservative, then the value of the integral only depends on the endpoints. It doesn't matter how you got there. Right? So if f is a conservative vector field, if you have your two endpoints, x naught, y naught, x1, y1, you can go any way you want, and the integrals are all going to be the same. So the integral along that curve is going to be the same as the integral along that curve, which is going to be the same as the integral on the straight line between them, which is the same as, sometimes it makes sense to actually break this up and do part of it just in the x direction, and then part of it just in the y direction. All of these curves, so long as they're oriented the same way, will yield the same value for the line integral. And so if you have some path that you don't like, you can swap it out for a better path and get the same thing, so long as f is conservative. And so it is critically important that f is conservative here. And so this is one of the reasons why we like conservative vector fields. It makes the line integrals nice. So let's now use the fundamental theorem of line integrals on that vector field that we were using before. So f is y squared 2xy. I think it's not too hard to find a potential function for this. So if you integrate y squared in terms of x, you're going to get xy squared, and that's the same thing as if you integrate 2xy instead of y. And so since those two match up nicely, that's our potential function. And so then if we're integrating f dr from these 2 points, so remember our starting point is 0, 0, and we're going to the point 1, 2. Well, so then this is going to equal to phi of 1, 2 minus phi of 0, 0. And so if I plug 1, 2 into there, I get 1 times 2 squared minus 0 times 0 squared, which gives me 2 squared, which equals 4. Same thing that we got from actually doing the two line integrals. That is all I have for you for this video. I will see you again soon.